So one thing I want to mention about tests in advanced math is that you're going to find that they have a certain structure to them. And one of those concepts is that the first page of your typical advanced math test is going to cover almost only really core basic concepts. And you'll often find that that first page is worth half of the test points. So it's really important that you understand what's on that first page. And for the most part, this first page is looking at function transformations that involve horizontal or vertical shift and horizontal or vertical stretch, and a few that involve a combination of some sort. And if the combination one looks like it's going to be tricky, you could save that one for last, and you might, by process of elimination, start to figure out what the answers are. So we have in the upper right corner the parent function, and we have all the way around here a series of transformations of that parent function. You have to pay attention to the grid. Sometimes the grid is in units of 1, and sometimes the grid is in units of 2. So for strategy for this one, what I'd like to do is look at the function transformation, think about what the graph should look like. So f of 2x, I've got 2 inside the parentheses. So what should that do? Something horizontal. It's not going to be a increase by a factor of 2, but a decrease by a factor of 2. Kate, you can't do math. Okay, so we're looking for a picture here that's going to be the same as the one in the upper right-hand corner, except it's been squished horizontally by a factor of 2. And, well, it looks like I down here. So I'm going to cross that one out. And I'm going to put I in the answer here. That doesn't help much. Next, f of x over 2. So that's actually the same as saying f of 1/2 x. So it's sort of like f of 2x, except it's 1/2. So instead of being shrunken horizontally, it's going to be expanded by a factor of 2 horizontally. So again, we look around for h. H, yeah, definitely expanded. So put h in there, and we can cross out h. Now we have a multiplier on the outside of f of x. So we've got 3 f of x. So since that's taking the result of the function, the result, what comes out of the function is a y-coordinate. We're taking the y-coordinates and we're multiplying them by 3, so we should get something that's been expanded vertically by a factor of 3. And if I want to, I can think about writing a little note for myself. This is going to be a stretch by a factor of 3, and then I go hunting for that. Well, e certainly looks like a vertical stretch. It's a very tall version of the parent function, so let's call that e. And then we have, oh dear, we have something that's been shifted. Yes, Spencer.
On number 2,
Mm-hmm.
you said for the stretch of a factor of 3 for e, or 3, would you just say like a horizontal progression for number 2, or would you do a
So for number 2, because the multiplier is within the parentheses, it has the opposite effect that it would have outside the parentheses. So here we have 1/2 of x. So you might,
horizontal?
so it's going to be a stretch.
Yeah.
So it's going to be enlarging by a factor of 2.
But you could just say horizontal stretch.
Yep. Yep. So again, number 4, we've got a horizontal shift. So I'm just going to make a note. Which direction is it going? X minus 3. It's going to go to the right. So I'm thinking it's going to be to the right by 3, and the plus 2 is on the outside of the parentheses, so that's going to be moving up by 2. So I want right 3 up 2. Oh, is that it right there? D, yeah, D is over 3 and up 2. Great. Goodbye, D. And F, oh dear gosh. So one thing you can do with f that's very useful is to rewrite this a little bit. So factor out the 0.5. It's really the same as 1/2 of x plus 2. So what that's telling me is that, again, the 1/2 is a multiplier inside the parentheses to give me a horizontal stretch by a factor of 2. And the plus 2 inside is giving me a shift to the left. So I want something that's shifted to the left 2 units and then stretched horizontally. I seem to have a recollection of seeing something like that down at G. So if you look particularly at this little vertexy thing here, that's been moved left by 2 units, and from that point, everything is 2 units wider. And then, oh good, we're getting back into some easy ones. F of x minus 4 should be a shift down by 4, so we want to look for that. That should be a nice easy one. Looks like get over here at f. 7, f of paren x minus 1, that's just a horizontal shift to the right of 1 unit.
Mr. Jensen, I have another question.
Yep, go ahead.
So for 5, since there's a fraction in front of x, that means the second number in the parentheses has to be has to have is that fraction of the actual number you're shifting it by. So since 1 is 1/2 of 2, you have to shift it by 2.
Right, right.
And if it was 3, you have to shift it by 6.
Well, so the reason they rewrote it as 1/2 of paren x plus 2 is whenever you're trying to evaluate a combination horizontal stretch and shift, to actually see that shift as the number you're looking at inside the parentheses, it has to be, the first thing you would evaluate would be the x minus 2 or the x plus 2. And so I need to rewrite that so that that x, in this case plus 2, is in the inner set of parentheses. So that gets evaluated first. And then I would see, again, if I look at the so-called...
It says plus 1.
It does. So by taking that 1/2 out, I factored it out. I factored it out of the thing.
Oh, so you multiply it by
Yeah.
1/2.
Right. So if you multiply that 1/2 into that x plus 1, x plus 2, you get 1/2 x plus 1 again.
Okay.
So it's useful if you see a bunch of these to sort of practice undoing them so that you can write it in the multiplier, then paren x plus or minus some number.
So 1/2 just goes outside of it.
It goes outside of an inner set of parentheses, but it's still all together inside the parentheses that go with the f. So if you look at the f,
Just take it out and then do the shift and then
yep. So it's still, everything is still inside the f parentheses. And so that 1/2 is still going to give you a horizontal expansion, horizontal stretch. But you can more easily see what the horizontal shift is going to be when you rewrite it like that. And the other approach, frankly, would be to look at the original function, f of 0.5x, and say, well, that's 1/2 x. So right away, I know that's going to be a horizontal stretch of factor of 2. And then the plus 1 is telling me it's going to be shifted to the left. So I look for something shifted to the left that's been expanded by a factor of 2. And again, I think there's only one thing that really fits it.
Okay, thank you.
Okay, good. Back to number 7, we're looking for a horizontal shift to the right of 1 unit, and that looks like B. And 8, what is 8 going to do? Somebody said backwards. So it's not a horizontal stretch, but it is a horizontal effect. It's going to be a horizontal reflection over the y-axis, and that looks like it's going to be J. So if you look at J and the parent function, they're mirror images of each other, and that's what happens, mirror images left and right, and that's what happens if you have a negative in front of the x inside the parentheses. And get rid of J.
So that's called a horizontal reflection?
Yep. Or just to confuse you, it's a horizontal reflection over the vertical axis.
Okay.
And Now we have an interesting one. We've got a negative outside the f, so it's going to take whatever comes out of the function and make it negative. So the parts of the original parent function that are above the x-axis go below the x-axis, and the part that were below the x-axis go above the x-axis. So it's a vertical reflection over the horizontal axis. And then, just for a little extra spice, we have a shift to the left. So we're going to do a left shift of 2 plus this vertical flipping thing. And probably the vertical flipping thing is going to be the part that gives it away. And we're looking for things that have been already not been crossed off yet. And this is a confusing one because it's A, which is shifted to the left, and it's upside down. And the problem with A is that it's clipped off the rest of the function. But it is what we want for this one. So A is the one. And, you know, by this point, we've crossed out everything, right? So absolute value of f of x, all you're saying about this is if you go back to the parent function, any part of this function that goes below the x-axis is negative. And if you're taking the absolute value of f, you're just going to say those negative things, they turn into positive things. So you could sketch it right on this parent function graph and say, well, the parts that are already above the x-axis, they're fine. The part that goes below is going to be flipped above. And so we look for one that matches that, and there it is, it's C. And we're done with that page. Is that all right? Okay. Okay. Part 2. Given the parent function, that didn't help. Forget that. Given the parent function f of x equals x squared. So we're working with a basic parabola. We want to write the transform function. So the curve in bold is the transformation. There's a light function drawn in there, which is the parent function. So it's really just a matter of looking at how this function moved from one place to another on this graph. And so this one has moved to the left by 3 units, and it's moved up by 2 units. So as a transformation of f, I've got g of x equals f of x, and a leftward shift is going to be x plus 3. And then if we're moving up, we're taking the output of the function and we're adding 2 to it. Similar vein, I want to also, I'm looking to see if it's did any stretching. It doesn't look like it's done any stretching. And this is a little tricky because if I'm looking at the parent function, I didn't quite hit it, at its vertex, if you go over 2 units on this graph, you go up 4. So 2 squared is 4. That makes sense. So on the transform function, I want to look at the same thing. If I go over 2 units, that's 2 units, and then up 4, I'm landing on the function again. So it's got the same proportions as the original one. So there's no horizontal or vertical stretching going on. So it's just a horizontal and vertical shift. So this one has been moved to the right by 4 units, and it's been moved down by 6. So it's really kind of the same as the previous one, f of x minus 4 this time, and minus 6. So we've kind of covered the bases for all kinds of horizontal and vertical shifting in either direction. And then this is interesting. So it's definitely been shifted down. If I look at my vertex has gone down by 4 units. So it's down by 4. But does it have the same proportions? Again, the apparent function, if I go over 2 units, the function goes up 4. So again, it's x squared. On the transformed version, if I go over 2 units, I have to go up 8 before I hit the function. So instead of 4, it's 8. So I have a vertical stretch by a factor of 2. So that's going to be vertical stretch times 2. So to make a vertical stretch, I need a multiplier that's outside the function. So I'm taking the output of the function, multiplying it by 2 to get that vertical stretch. Inside, I'm not doing anything horizontally. There's no stretching, there's no shifting, so it's just f of x. And then on the outside, again, I want to subtract 4. That brings it down. Next one, we have sort of a different set of axes. We've got a single unit per grid square. Parent function, over 1, up 1, over 2, up 4. The transform function is upside down, so right away I know it's going to be negative f of x. But it also has a vertical stretch going on. If I go over 1 unit, it looks like I'm going down a half. So a half right there. If I go over 2, it goes down 2. Now if it were a regular parabola, it would be over 2 down 4. 2 squared is 4. So this is over 2 down 2. So it's moving vertically half as much as the parent function does. So that's a vertical shrink. So there's 2 things going on. There's no horizontal thing going on. You have g of x equals negative. That makes it go reflected over the x-axis 1/2. That gives me that squishing effect. And then f of x. So the original function f of x times negative 1/2. Spencer?
So for 2 and 3, I originally did f of, I originally did f of 2x minus 4 and negative f of 1/2 x. And it like essentially comes out to the same thing, right?
And similar, if you have, think about it, if f of x represents x squared, so to write this in terms of just x by itself, I'd say this is 2x squared minus 4. Now, you could,
Like if you just did the function as f of 2x minus 4, wouldn't that end up with the same?
not quite. So let me rewrite this by putting parentheses around this. In order to get the same effect, I'd have to write paren square root of 2 x paren squared minus 4. So do you see how these 2 expressions are the same?
Yes, I do.
Right. So square root of 2 squared would be 2, and that would give me 2x squared. So this is the same as saying f of square root of 2x minus 4. So yeah, you can do this as a horizontal shrink, but you have to be a little bit, you have to pay attention to what the function is doing, because putting the constant inside there, it's going to end up getting squared. So it's a little tricky,
Okay.
a little tricky. So you have to be thoughtful about it if you're going to try that with a quadratic. Can be done. Any questions, other questions about page 2? All right. Here we have a question about inverse functions. So we've got a function f of x equals 2/3 x plus 4. Okay, so this first one's pretty straightforward. Verify that f of 9 equals 10. Okay, so I say f of 9 equals 2/3, and I'm just poking 9 in wherever there was an x, times 9 plus 4. The 2/3 of 9 is 6, so that's 6 plus 4 is 10. Yep, okay, so 10 equals 10. Good. Algebraically find inverse f of x. So that's this trick where you rewrite this f of x equals 2/3 x plus 4 as y equals 2/3 x plus 4, and then swap the x's and y's. So that gives me x equals 2/3 y plus 4. And now I want to solve this for y. Why? Because that's what you do. So we're basically just flipping the x and y and rewriting it as a y equals kind of thing. So let's see. I can rewrite this as 2/3 y equals x minus 4. And if I multiply both sides by 3/2, I'd get y equals 3/2 x minus 4, which is correct. I could also distribute the 3/2, and I'd have 3/2 x minus 6. So that's, let me rewrite this formally. So f of inverse f of x equals 3/2 x minus 6. And then we're going to see if it's right. Let's see. So if I put 10 in there, it should give me 9. Oh, goody. Notice that in the first one we did f of 9 equals 10. So an inverse function should work the reverse way. F of 10, or inverse f of 10 equals 9. So all we're just doing is seeing, does it really go backwards? So it's the same idea. Inverse f of 10 equals 3/2 times 10 minus 6, which equals 15 minus 6, which equals, oh, thank goodness, 9. So that's 9 matches, we're good to go. Questions? Okay. For the graph of y equals f of x, whatever this thing is, carefully sketch the graph of the inverse. So we haven't been given this function in sort of an algebraic sense, so we can't do this, switch the x's and y's things, but we can do this graphically. And a good technique would be to do a reflection over the y equals x line. So I'm going to draw in a little dashed line for the y equals x. And I'm just going to take points that I identify on the original function, so like that one there, and put their mirror image on the other side of that dashed line. And here's when it goes through 0, 1, so that's going to be at 1, 0. And then we're going up here, we're at 1 point something 3, so that'd be 3 comma 1 point something, that would be right about there. So I've got 3 points that I've mirrored across this diagonal. That's enough for me to make a pretty good sketch. Just going to pass through those points. So this represents inverse f of x. Questions? So this question is asking you to think about what are the effects of this various constants when you're doing a transformation. So this is sort of symbolically showing you a transformation from hell, where every possible thing has been shown. And we want to think about what all the effects are. So the a and the b, these are constants that are outside the parentheses, so they're going to have an effect on the vertical position of the transformed function. And so one way of saying that would be that you're going to multiply every y value that comes out of the function gets multiplied by b, and then add a. Horizontally, it's a little more interesting. So this is shown, notice, in this form. Go back to the first page when we converted 0.5x plus 1 into 1/2 of x plus 2. So again, getting inside the parentheses for the f, we've got an inner set of parentheses, and that helps with the interpretation of what's going on. So horizontally, we want to multiply x values, not by c, but by 1 over c, and then subtract the d value. You could also think of this as just c is the horizontal stretch and d is the horizontal shift. Spencer?
So is this graph going like, pretty much like going horizontally, not vertically? Because if f, like if the function of f is equal, or like where's, oh wait, never mind.
So this is just, this doesn't suppose any particular shape for f. It just says for any function, if you want to think about, if you're seeing a transformation written like this and you have numbers shown for a, b, c, or d, what you want to be able to do is picture how the original function has been changed as a result of some number for a or b. And everything we've done so far in this review or test, we have been using this idea already. And so this is just rolling it up as in, like, well, summarize for me what you think.
Like f of x equals, like it's something with x, but this says f of x equals y.
Yeah, so we've got some parent function f of x. I don't know what it is. Could be x squared, could be square root of x, could be e of x.
So the y on the left, is that like the vertical line?
Yeah, the vertical position. So whenever you have an f of x, the implication is that what comes out of that function is going to be the y, the vertical position, the y position on the graph. So it would be normal to say y equals f of x.
Okay. So we also do like x equals, let's do like x. Oh, wait.
So x equals f of x would be
Yeah,
pretty
just get, like,
confusing.
a deep- yeah.
Okay.
Thank you.
And now, the ultimate fun. So you may have noticed as we're going through this review that the questions are getting a little bit harder. This one is the hardest of all, maybe. So the parent function here is the square root of x. If I'm looking at the expression on the right that's g of x is equal to, so g of x is equal to the absolute value of square root of x plus 4 minus 3. What I'm thinking to myself is, oh, that's the absolute value of f of x plus 4 paren minus 3. So the part that's inside the absolute value bars is just f of x plus 4 paren minus 3. That part's easy. That just says I'm going to shift to the left 4 units, and I'm going to drop it down by 3. Oh, okay. So when I'm done with that, I could worry about the absolute value part. But before I do the absolute value, it's just a horizontal and a vertical shift. If only I knew what the square root of x looked like. Well, can you take the square root of a negative number? Sort of. We can't graph it on this plane. But square root of 0 is 0, so I got a point there. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. So I can sketch the parent function. Very nicely leaving little gaps for me. Thank you. So that's f of x. So now, let me do the inner transformation of f of x. So that's going to be a shift to the left of 4 and down 3. So my beginning point, I'll change the color too. let's see, green, okay. So my little vertex here at 0, 0, I'm going to move to -3, -4 on the x-axis and down 3 on the y-axis. So there's my starting point. And then it's going to go over 1, up 1, over 4, up 2, over 9, up 3. All right, 5, okay. So I've got the corresponding points have been plotted, and then I can connect them together the same way. And it's important to notice that this point at x equals 5 is where the function crosses the x-axis. So everything to the left of that point, everything to the left of x equals 5 is below the x-axis. It's negative. And that's important because the very next thing we're going to do is we're going to apply the absolute value function. So the absolute value function is now this part of my green curve. And everything that's above the x-axis is fine. It's positive. It doesn't get touched by the absolute value function at all. It leaves it as it is. So in my final version of this, I can just draw that red curve going above the x-axis there, because that's what it should do. But here I should be bouncing off. And so I'm going to make a mirror image of the green that's below the x-axis. I'm going to make a mirror image above the x-axis. And I get something that looks like this. So when I'm done, I can erase these things that I used to get started. Why can't I erase that? Anyway, okay. So finally, my very last step, I'm going to make a label here that says this is g of x. And it does go off to the right forever, and it does stop at x equals -4 as we go to the left. Some questions? So I'm not 100% sure, but I think I've been recording this. And if I have, I'll try to put a video online that you can get through for Schoology if you want to see this again. Hmm?
The interwebs.
The interwebs, yeah. Otherwise, we'll have a test on this tomorrow. Have a great day, folks.
You as well.